Hello and welcome to the presentation. I'm Nguyen, a research fellow at CREST, the University of Adelaide, and I research on secure and trustworthy software systems based on decentralized technologies such as blockchain. Today, on behalf of my colleague, Professor Ali Babar, I'll present our research on how blockchain networks can be designed for use cases at the network's edge. I would like to start with an observation. Despite being commonly criticized as slow, inefficient, and even wasteful, blockchains have been enjoying a steadfast interest from use cases at the edge. This interest is not limited to Internet of Things applications, which tend to rely on cloud infrastructure. Blockchains have also appeared in other domains that employ edge infrastructure with limited resource, even mission-critical systems. So, how are these edge blockchain networks possible? Are they a result of novel consensus protocols or careful design decisions? In this research, the term blockchain network denotes a distributed system, not its underlying TCP/IP network. A blockchain network comprises multiple computer processes, or we can say nodes, which are connected by a computer network. Together, they maintain and update a replicated list of transactions, without involving a trusted third party. An edge blockchain network has two additional characteristics. Firstly, it is employed to decentralize and improve security of information and processes at the edge, such as authentication, authorization, provenance, and trading. Secondly, its elements are spread across an edge infrastructure, including clusters of edge devices, fork nodes, and cloud infrastructure. As a result, edge blockchain networks features a significant number of design decisions. In this research, we explore how edge blockchain networks have been designed. We identify common sets of design decisions and codify the design knowledge into design patterns in order to guide future research and development projects. We use edge blockchain networks that are employed by primary studies in edge computing and related domains such as Internet of Things, cyber-physical systems, vehicular networks as the data of our research. We decompose these designs into design decisions and identify patterns from the extracted decisions. To ensure the objectivity and replication of the research, we employed a procedure inspired by the systematic literature review method. By following the described procedure, we identified 12 design patterns. We classify these patterns according to three features. Logical topology describes how a blockchain network is structured at logical level. In other words, it describes whether a blockchain network comprises one or multiple separate sets of transactions. Deployment structure describes how blockchain channels can be spread across an edge infrastructure. Finally, consensus describes the type of consensus protocol that is closest to the edge. We named the design patterns according to these three features. To clarify the concepts, let me describe one of the most prominent design patterns from the data, which is called cross-cluster fork proof-of-work design patterns. As a cross-cluster patterns, this design consists of one blockchain channel that spans multiple clusters of edge devices. In other words, there is only one set of transactions, or one global state, that is shared among all participants in an edge infrastructure. As a fork pattern, both minor and full nodes of this design reside on fork nodes of the design cluster. In other words, fork nodes store the entire transaction history and are responsible for processing new transactions. Finally, as a proof-of-work pattern, miners repeatedly try to solve a cryptography puzzle in order to win the right to process the next batch of transactions. This is the same consensus mechanism that is used by public blockchains such as Bitcoin and Ethereum. This design pattern can be implemented entirely by off-the-shelf blockchain components, just as the Go implementation of Ethereum. Despite this simplicity, this design pattern was the most common design patterns across the evaluated papers. So, in summary, we found that edge use cases generally establish new blockchain networks, or at least new blockchain channels running in parallel to a public blockchain, rather than relying solely on the public blockchain. Many edge blockchain networks rely on careful design decisions that harmonize their requirements with the resource of an edge infrastructure and the limitations of a blockchain. rather than relying solely on faster and cheaper consensus protocol. So, future research would focus on making the design knowledge from this taxonomy actionable. The first step would be to evaluate the design patterns with experiments to build an empirical understanding of the quality of these patterns. This knowledge would provide input for a design support framework, which guide developers toward optimal network designs based on their requirements in terms of the organizational structure and the infrastructure that they have. With these implications, we conclude the presentation. Thank you for your participation.